Hey guys, welcome to another video on our new unit. Today we're going to talk about ionic bonding. So before we get there, what I wanted to talk about really quickly with y'all is I wanted to talk to you guys about some things that we've already learned. So let's start with these questions. Go ahead and answer them to the best of your ability. Awesome. Hopefully you took the time to answer it. Let's go. First question is, how many valence electrons do noble gases have? The correct answer would be they have 8 valence electrons. Yeah, remember, wait, actually, that's something we're going to learn in the future. How reactive are noble gases? We know that they're very unreactive. And then the last two questions are asking for orbital diagram shortcuts. So you'll notice that for chlorine, the orbital diagram shortcut is 3s with 2 and then 3p with 5. For sodium, it's going to be neon and then 3s1. Hopefully what I want you to notice about chlorine and sodium here is that they both are based in neon, and then chlorine is almost argon's electron configuration. If it gets one more electron here, it'll become argon. And sodium's electron configuration is almost neon. If it loses this first electron, this first arrow here, it'll become just regular old neon. What we're going to be talking about are ionic bonds. Ionic bonds form when atoms like chlorine and sodium either gain electrons or lose electrons. So that's kind of a little preview of kind of how it happens and what it becomes. Let's go ahead and let's continue on. So the question is, how can these elements become stable? Stability, remember, is what we get when we're a noble gas. So chlorine is going to gain one electron, right? Here's its normal orbital diagram shortcut. What's going to happen is we're going to take that arrow and then move it into the box. That was supposed to move into the box. Sodium's going to lose one electron. Here we have it removing that electron, and then what you'll notice here is in both of these pictures as well, that's just showing how in this case sodium loses one electron and it then has a stable 8 around it, just like neon does. Or in this case chlorine, you'll notice that it gains an electron and now it has the same number of electrons as an argon would. So by chlorine gaining one electron and sodium losing one electron, they both become stable. They both become like noble gases in their electron configuration. And it turns out that's what ions do. Atoms either gain or lose electrons to become more like noble gases, which makes them stable, makes them less reactive. Okay, protons versus electrons. Remember, electrons determine reactivity and protons determine identity. That's important. All we're talking about here is we're talking about electrons. Never will we ever talk about atoms gaining or losing protons, just because we don't see that happen. We do see them gain and lose electrons, though, because they're on the outside. Oops. An ion, some things you want to know, some things you want to write down about an ion, is that it's got the same number of protons as a regular atom does. But the important thing now is that the difference between, say, a chlorine atom and a chlorine ion is that a chlorine ion is going to have a different number of electrons than a chlorine atom. And then remember, the reason why we become an ion, why an atom would become an ion, is to become stable. So all these 3 bullet points are kind of the 3 main points you want to have written down in your notebook about ions. Okay, sometimes it's hard to visualize how by adding electrons you become negative, but that's true. Let's imagine here that you have 5 positive signs and 5 negative signs. In this case, the positive signs, of course, represent protons, and the negative signs are going to represent electrons. Now, what I want you to notice is as I add electrons here, notice now how I have 6 and 5. My total charge is going to be -1. So even though I'm adding electrons, what I'm really doing is I'm making my charge more negative. And then you can see I can add more, and it becomes -2 or -3 or -4. Now, we'll also talk about removing electrons, and what I want you guys to remember is when we're removing electrons, that is a positive action. Think about it. Here we have a regular atom. It's got 5 positives and 5 negatives, just like a regular boron atom would have 5 protons and 5 electrons. If we remove 1 electron away, now we've got 5 protons but 4 electrons, so our total charge is positive 1. We remove 2, positive 2. Remove 3, positive 3. Remove 4, positive 4. So hopefully this shows you how even though you're hearing phrases, you'll hear phrases like add electrons or remove electrons. You might think adding is always positive and removing is always negative. That's actually flipped because remember, electrons are negative. So if you're adding something that's negative, you're going to get a more negative charge. If you're removing something that's negative, you're going to get a more positive charge. So the moral of this story is if we add 1 electron to chlorine, remember that makes it stable, it becomes Cl1-. If we remove 1 electron from sodium, now we're getting a positive charge because we're removing that negative thing. There's 2 types of bonds. There's covalent and ionic. We're not going to talk about covalent bonds. We're only just going to focus on ionic bonds this unit. Next unit, we'll talk about covalent. So some things you need to know about ionic bonds. They form from ions. So you're going to need a positive ion and a negative ion. Those 2 things are going to attract to each other. Think about this like magnets. You know, you need a north pole and a south pole in order for them to come together and attract. The phrase is opposites attract here. You need a positive charge and a negative charge. Those attract. Just like they do in electricity, just like they do with magnets. The opposites in this case attract. Metals usually form positive charges and nonmetals usually form negative charges. You're going to want to write this first and second bullet point down, guys. The other thing to know, and this is the most important, this is what we'll spend the most time working on, is that once you take your positives, you have to merge them with an equal number of negatives. And that's going to form your neutral compound. So let's say your metal has a charge of +1. You're going to need, for every 1 + 1 you have, you're going to need 1 negative ones. But let's say you're dealing with an ion that has a higher charge. Maybe you're dealing with like a -3. Then the question becomes, well, how many +1s do I need? I'm going to need 3 1+ ions to cancel out my 1 3- charge. As you can maybe tell, that gets a little bit more complicated. So what I have next for you guys coming up here is some examples of how to form neutral compounds. These 4 atoms have all turned into ions. You'll notice that there's little purple charges next to each one. What I want you guys to do right now is think, how many sodium +1s and how many O2- would I need for them to be neutral? And then think, how many Fe3+ would I need for every O2-? Let's go ahead and do the first one together. Both of these should be in your notebook. Okay, so Na1+ and O2-. Now, here's the goal here. I know that if I add another 1+, my total charge is going to be +2, and my total negative charge is going to be -2. That makes them neutral. So, I know that I need 2 sodium 1+s for every 1 oxygen 2-. How we write that as a formula is we would write something that looks like this, Na2O. So this Na2O is the chemical structure of what happens when you mix sodium with oxygen. It forms Na2O. With iron and oxygen, it's a little bit different. Go ahead and try it out. Pause the video. Awesome. Hopefully you got a chance to try it. Let's go through it. For iron and oxygen, I'm going to need 2 irons and 3 oxygens. That's going to bring my total positive charge up to +6 and my total negative charge over to -6. So there's my 3 oxygens, 1, 2, and 3. There's my 2 irons. So my formula would be Fe2O3. This is also called iron 3 oxide. We'll talk about how to get the names eventually. We'll eventually get to that. Okay. Yeah, that's the same slide. Moving on here. Great. 2 more examples for you. Hopefully you didn't see the answers on the other side. Go ahead and try these out, please. Awesome. Here's the one for manganese and nitrogen. Notice here how I'll have to have five nitrogens and three manganeses so that my charges on either side are 15. 3 times 5 is negative 15, and 3 times positive 5 gives me positive 15. Over here, 6 plus and 2 minus, I will need 3 sulfurs and one of these one of these tungstens. So that gets me 6 on each side. So my formula would be WS3 and MN3N5. Hopefully you feel a little bit more comfortable about creating neutral compounds. This is the key for ionic bonding. If once you understand this, everything else is going to be a lot easier to understand. All you have to do is make the number of positives the same as the number of negatives so that they equal 0 and that they're neutral. If you still have a positive number that's greater than a negative number, then you'll have a positive compound. If you have a negative number that's greater than the positive number, then you'll have a negative compound. We want neutral compounds. That's the goal of ionic bonding. So you'll notice that they come together in unique ratios. Also, you'll notice that there's probably more than one way you could get W and S to be neutral. For example, you could do W2S6. The formula we write down is always just the lowest formula we need to write in order for it to be neutral. So in this case, having one W and 3 S's is the lowest form possible. Okay, now we're going to kind of move into day 2 stuff where we talk about properties of compounds. Ionic compounds are hard, but also brittle. So think about things like table salt, right? An individual granule of salt might be very hard, but you can crush it fairly easily. It doesn't bend is kind of the idea here. That's what brittle in this case is standing for. It doesn't really bend. It's not malleable, so to speak. They melt at extremely high melting and boiling points. Yeah, I think it's like 3,000 degrees Celsius, or at that point Fahrenheit, realistically. It's pretty much the same. They're solid at room temperature. That makes sense if they have high melting points. The other thing that ions do very well is they dissolve in water. So, pretty fun. And then lastly, of course, it is a strong bond. That's not super important. But it is important to know that they're solid at room temperature and that they're very hard and brittle, and also that they dissolve. Okay, here's the idea here. Ions are charged atoms, and then the other thing you need to know is that if you change electrons, you're going to change stability, right? So that doesn't always mean that adding more electrons will make you more stable. It's whichever way you have to go, either adding or removing electrons to create a more noble gas-like number of electrons. So let's say you're at 12, the closest noble gas is 10, you're going to lose 2 electrons to get there. Let's say you're at 16, the closest noble gas would be 18, so you could either gain 2 to get to 18, or you could lose 6 to get to 10. You'd probably just gain 2. So it depends. Sometimes you'll gain electrons, sometimes you'll lose electrons. It's whatever the atom wants to do to become more like a noble gas, to become more stable. So electrons influence the stability of an atom. You change protons, you can't really change protons. Also, that just changes an atom in general. 2 words I'm going to throw at you, cation and anion. But before we do that, we're going to talk about noble gases. Noble gases are unreactive and very stable. It's due to their electron configuration. Here's the electron configuration of He. That's helium. Neon's the next noble gas. Here's its electron configuration. I'm just going to show you all of them. One of the things I used to say is that they all have 8 valence electrons. If you look at helium, that's not really true. They don't all have 8 valence electrons. Helium only has 2 valence electrons. What I'll say to you now that is always true is that they all have these things called full outer energy levels. So helium has a full energy level 1. You can only fit 2 electrons in your first energy level. Helium's got it. In every other energy level 2, 3, 4, and 5, you can fit up to 8 valence electrons. So we sometimes say all noble gases have 8 valence electrons. That's not 100% true because helium's weird, but it is 100% true that all noble gases have full outer energy levels. Those full outer energy levels means they don't want any more electrons, they don't want to get rid of any electrons, they don't want to add any electrons, so it means they're stable and unreactive. All ions kind of want to become that way. And then when they become that way, they get these positive charges, which forces them to attract to each other. That's how ions work. Cool. Okay, here's another thing we're going to throw a lot at you. Octet rule. So sometimes we'll just say, for the sake of it, we'll shorten our idea of full outer energy level to stability. Sometimes we'll just say octet rule, which means atoms react to get 8 valence electrons, right? So in this case, sodium wants to get rid of that 3s so that it's got the full 2 energy level. That means it loses 1 electron, it becomes like neon, it's stable. Chlorine in this case, almost like argon, it's going to want to gain 1 more. That makes it like argon, now it's stable. So this thing called the octet rule, also known as the stable 8, it means that atoms are going to react to get 8 valence electrons. They want to be stable and they want to have 8. So please write octet rule down in your notes. Okay, cations are positively charged ions. That's how I remember it, positive, if that's helpful at all. Another way of thinking about this is, look, you're losing an electron, you're losing something that's negative, you become positive. So cations are ions that lose electrons, and they are positive. Another way of thinking about this, if you're losing electrons, that means you have more protons and less electrons. More protons, more positive. Positive, like pause. Anions are negatively charged ions. This is Anne Hathaway. Negatively charged ions, they have more electrons than they have protons. So anions are usually nonmetals. Cations are usually metals. Fun fact. So in this case, we have chlorine. Chlorine is a cation. It'll gain an electron to have 18 electrons versus 17 protons. That means it's negative. Here's how I remember it. This is the lady yelling at the cat meme, and you've got the lady as an ion, she's negative, and the cat is positive. I think that's funny. Anyways, moving on. Here's a really fun table. Go ahead and try this out. We have before ionization and we have after ionization. Actually, let's go ahead and work through the first one together. So, the ion formed, we're just going to write down the symbol, which in this case is going to be iodine. And then if you look in the periodic table, iodine is actually in that halogen row. It's got 7 valence electrons. It wants 8. So it's going to form I1-, just to get that 1 extra electron. What that means is it means its number of protons are the same, 53, has not changed. But its number of electrons is going to be 1 higher, 54, because it's got that -1 charge. That means it has 1 more electron than protons. And now the question is this a cation or an anion? And the answer is anions are negative, cations are positive, so this would be an anion. Go ahead and use this slide, figure out what would the symbol be for beryllium, and then how many protons would it have and electrons would it have after ionization, and then is it an anion, is it a cation? Go ahead and try that out. Hopefully you got Be2+. Hopefully you said it had 4 protons and 2 electrons. In this case, it wants to become like helium. Helium is the closest noble gas. The other noble gas closest to it would be neon, which had 10. So it's either lose 2 or gain 6 in this case. And it's going to become a cation because it's positive. We're not quite done with this little table. So hopefully you drew it down. Hopefully you wrote this all down. Because here's what I want to show you is an even bigger table. Now we've got lithium over here. We've got whatever has 7 valence electrons. You should be able to figure that out. Then we have sulfur and strontium. Go ahead and use your knowledge of before ionization and after ionization to complete this table. Awesome. Lithium, 3 protons, 3 electrons. It's going to have 3 protons before and 2 electrons afterwards because it wants to become like helium. Helium has 2 valence electrons. That means the ion formed is going to be Li1+, which is a cation because it's positive. The next one, 7, that's nitrogen. Nitrogen has 7 protons and 7 electrons at the start. It then goes to 10 electrons at the end. It gains 3 electrons, meaning its ion will be -3, and it's an anion. Here's sulfur and strontium. Hopefully you got all this. If you have questions, please let me know. Here's what I want to focus on. I want to focus on how do you notice that number of protons and electrons are the same for atoms normally? That's true. That's always going to be true. Do you notice how the number of protons stay the same while ionization happens? That makes sense, right? Ionization, protons don't change. What does change? We're looking at electrons. Electrons change, and they're going to convert to the closest noble gas. If you look on your periodic table, you'll notice that the 4 earliest noble gases have 2, 10, 18, and 36 electrons total. So that's helium, neon, argon, and krypton. These other elements become like these closest noble gases because those numbers of electrons are stable, right? They all have 8 valence electrons or a full outer shell, meaning they're stable, meaning they don't want any more electrons, they don't want any fewer electrons, so they won't react any further. That's what I wanted to show you as kind of patterns. These are patterns that will always be true. If you have an atom, it's going to have the same number of protons and electrons at the start. If it turns into an ion, the number of electrons is going to convert to the closest noble gas. The number of protons stay the same. Hopefully this helps you understand ions a little bit better. Hopefully you feel comfortable taking on the homework and daily assignments. Please let me know if you had any other questions. Thank you so much for your time. Have a great rest of your day.